Here's a bit of a question that I think you should be prepared for. Because if I can think of this question, then they can think of this question. Now, earlier in the week, we did a problem that looked just like this, and or I guess it's like 2 weeks ago. So I want to call your attention to the problem we did in class. It started out with a mass on a spring, and then I can see it just fine. I don't know what your problem is. Look closer there. Now, is that a problem? It's probably going to be a problem. Fine. Did you know that's like the third time I've done that today? You should expect more from your teachers. But you know it's really hilarious. You kind of told me right away. In the other class where this happened, they didn't say anything until I got like 5 minutes in. It was bad. So that was kind of funny. It says it's connected, but there's no evidence of that. So I'm going to have to stop it and start it again. Oh, Zoomy. You're not written by the lowest bidder, but you definitely have your shortcomings. We might not be doing this. Let's give it one more try. So to do what I have to do, I'm going to have to put something else up on the screen just so there's something there to unlock the Wi-Fi. So now you see my login for my email. Exciting, isn't it? Except that's not my student number. There we go. So now it's unlocked it. Here we go. That's better. All right, so in the one that we had to do, the mass was pulled back against the spring, and energy was added to the system, like so, and then the system was released. So that when the system was released, it passed back through equilibrium. And if you remember the problem I'm talking about, when it passed back through equilibrium, the mass was then traveling at its fastest, and it was at that moment that another block was going to be dropped on it. Do you guys remember this problem? Now, this is very much a short evolution of the problem you guys did as your FRQ for today. In the problem that you did for today, the difference was it was the mass on the spring that was at rest, and another box crashed into it. So the momentum, there's a conservation of momentum problem, a clear a clear energy question, and a relatively straightforward simple harmonic motion question. So the problem that we did 2 weeks ago did this problem in reverse, making the thing that was moving, the one on the spring, it got its energy from the spring, and then the colliding object was the object that was dropped on it. It would have been the same question had the box been placed here and this one collided at it if it hit it at equilibrium. It was distracting to have it dropped on it because it made you think, well, is dropping it somehow different? But if I had just placed a block right here at rest, that would be the same question. Everybody following along so far? Because here's where it's going to change. And the change is interesting. So what if instead of these situations, we don't have something drop on the box here and we allow the box to travel all the way to its other side? Because here it was, of course, pulled back a distance A. We know eventually it will make it to the other side, a distance A, away from equilibrium, and will come to rest here. What if I drop a box on it right as it comes to rest here? I'm asking that because I can imagine several variables: period, amplitude, momentum, velocity, kinetic energy that could be impacted by this situation. In fact, what I would like you to tell me is which of these 5 variables would be impacted, which one would be forced to change after the collision due to the block being, with the one block landing on the other block. I'm willing to take a volunteer where you can pick any one of these things and tell me what you think. I got a couple volunteers here, so go ahead, Luke. All right, so you're saying the period would increase because of and you're saying it because 2 pi times square root of m over k. Now, and I think there's absolutely nothing wrong with that. I think you're right, for one thing. But is there somebody who could offer a different explanation that doesn't reference the equation? Somebody else. Go ahead. Andrea? Oh, Andrea had her hand up first, but that's okay. Go ahead and finish the sentence. Make it a complete statement. Because I don't think that's enough. So let's hear the whole thing. You're right on it. Keep going. Keep going. All right. Well, I mean, all the things she's saying are correct, but she's not speaking to period. She's speaking to velocity. So there's nothing wrong with all the things she said, but it's important that we understand something that's happening here. She's saying that because it has more inertia, it will take, more energy to move it. I'm not sure if that's actually true. But like you said, it would take more energy to move it at the same speed as before, so it goes slower. That makes sense. You would have to say one more sentence then to indicate why the period would be affected. It's traveling slower, so it will take longer to go the distance. That's what I mean. You have to connect it all the way. Why does something going slower mean it takes longer for it to get somewhere? You have to make that inclusion. Don't make the judges say, okay, the velocity is less. How does that affect period? You need to be the one to say it. But I think you're right. And I think that's but you also spoke to this one. So, are we agreed the velocity will be affected? I think so. Now, I think after this, it gets a little bit more muddy. So let's see if somebody else wants to offer a different or an explanation about one of the other variables up here. Go ahead, Abby. Abby put her hand up, so I'm going there. Sorry. So, how many of you believe the kinetic energy is going to change because of the sudden increase in the mass? All right, excellent. Now, I purposely chose this because I knew it was going to kind of mess with your mind. All right, so it was like 3/4 of you said that, when I asked that, you're shaking your heads. The kinetic energy is not affected by this change. And I knew it was going to blow you guys away, or at least some of you. Now, I want you to think about this for a moment. When this box lands on the other box, at that instant, how fast was the bottom box traveling? That's right. So the velocity was 0, which meant that at this moment, the kinetic energy of the system is 0. Where's the energy? Okay, somebody typed it's in the spring. That's right. Which means all the energy is in 1/2 k a squared. Are any of these things affected by the fact that the mass changed? So when the spring suddenly has to move the box back, the energy's here. In fact, the same amount of energy will now be here when it passes through equilibrium. So the kinetic energy doesn't change. But the mass is suddenly greater. In fact, going back to what Andreas said, it's the fact that the mass is suddenly bigger, but the energy is the same, that makes the velocity less. Meaning, there's less velocity because I have a finite amount of energy. And as Andreas said, it's harder to move. And because the energy hasn't changed, the velocity has to decrease in order to deal with the increased inertia. You could also have said earlier that because it's harder to move and the force from the spring isn't any different, then it will accelerate less. Those are all reasonable explanations. But I think this would keep people off. In fact, I think it would purposely throw people off, which is why I wanted to have this as our example. An interesting thing is, did the amplitude change? No, the amplitude will be unaffected. What we don't know, actually, is this one. There's no way to know if the momentum is different. I think it likely is different, but the mass increased, the velocity decreased. It's plausible the value of the momentum might not be changed as much as we think. Now, we could find out. We could actually do the math and calculate how much the mass changed the velocity and then see if it affects the momentum. But I don't think we can make a reasonable critique of whether the momentum changed or not in this question. So I hope you see that this question tests the same ideas as that question, but does so in a way that is definitely requiring you to explain yourself, consider the reasonable choices that are here, and in many ways I think is much more challenging, even though you might not calculate or push one button on the calculator. Which is why I think this is a more likely question for the exam than what the FRQ was you did today. But they didn't ask this. This has never been asked on the exam yet. But I'll tell you what, if I was writing the exam, this would be the way to go. It's a solid question and it's not too challenging. All right? Well, we are into the no-no zone for time. It's ticking away with less than 5 minutes. So we are not meeting tomorrow because it's Friday. However, you guys still have kind of a good amount of MyAP homework out there. And I know some of you are struggling with the MyAP more than those FRQs. I have breakfast with my E&M group up until about 9:30. So I'll be available for tutoring from like 10 to noon. So if anybody wants to pop in, I think I put the link on the Week at a Glance, but if I don't, I'll put it in Edsby so you can just fire up a Zoom and it'll alert me that you're looking for a Zoom session. At the same time, I want you to consider that I have a 12 o'clock meeting that I have to attend with other AP teachers. And then afterwards, I don't know whether I'll be available or not. It really depends on how long that meeting goes. I'm going to try and get all the stuff that you guys have submitted graded this week. And also, some of you have had difficulty with MyAP. So after today, I will go and unlock all the questions that have been locked down, except for the one that I've assigned for next week. So that if you didn't get a chance to do one of these, try and go back in there and do it so that you can at least have the experience. That's about it. Monday, I think we should break out from our places. Some people in fifth period said we were getting too stagnant. So I'm going to be transmitting from a new location on Monday, like a little field trip. And somebody suggested the roof. That's unlikely, but maybe the hammock in my backyard, or I don't know. Maybe I'll just take everybody to the park with me, and we'll have a Zoom session at the park. Of course, that's going to use the data on my phone. Well, heck, I've been in the house so much, I probably have lots of data all saved up that I haven't used. So, there is that. But it's been great seeing you guys. I'm glad you guys can make it here for class. I hope you guys have a wonderful weekend if I don't see you. And of course, I'll see all of you on Monday, I hope. Xavier raised his hand. Yes, Xavier? Why is linear momentum not conserved? Well, the simplest answer is momentum's only conserved in situations where there's no net force acting on the system. But this system did have a net force acting on it. It was the spring. So although the mass fell and struck the other mass, the fact that at that moment when the collision occurred, there was no momentum because the velocity was zero. It is the spring that acts as an external force and causes a change in momentum of the system. And Abby saying, Mr. Sheldon, am I going to be added to the raffle? Yep, because you participated in class today and voluntarily asked a question. So you're in there. I think there's 8 kids in the raffle for juniors. They were pretty tight-lipped earlier today in class. So, and one of the kids that participated isn't one of my students, so I'm definitely not going to select them. So there you go. So you're 1 of 8. You have a 1 in 8 chance. So there was, 4 of you participated in this class. So there it is. Well, I guess I could also say that Victoria, she should be one. She let me know that my iPad wasn't working. Of course, then somebody totally slapped her for saying it. Nice. Nice. All right, so I will talk to you guys on Monday. Have a fantastic weekend, and I look forward to seeing you guys in a little bit. I miss you guys.